Light makes vision possible. Without it, nothing is visible. Objects are visible when light from their surfaces enters our eyes. Light also passes through transparent materials like glass or water. Light travels in straight lines, creating sharp shadows around opaque objects. A ray of light is its straight line path. Opaque objects block light, while transparent materials let it pass through. People have long debated what light is. Theories include the wave theory and the particle theory. Modern quantum theory combines these ideas, showing light has properties of both waves and particles, but is neither. Reflection happens when light bounces off a polished surface and returns to the same medium. Two laws govern reflection. The first law states that the angle of incidence equals the angle of reflection. The second law says that the incident ray, the normal, and the reflected ray lie in the same plane. When plane mirrors form images, they have four key characteristics. The image is virtual and erect. It is the same size as the object. The image is laterally inverted, meaning left and right are reversed. The image distance behind the mirror equals the object distance in front of it. A spherical mirror is shaped like part of a sphere. There are two main types: concave and convex. A concave mirror curves inward and converges light rays. A convex mirror curves outward and diverges light rays. The pole is the central point on the mirror. The center of curvature is the sphere's center. For concave mirrors, it's in front, and for convex mirrors, it's behind. The radius of curvature is the sphere's radius. The principal axis passes through the pole and center of curvature. The principal focus is where parallel rays converge or appear to diverge. The focal length is the distance from the pole to the principal focus. For small apertures, the radius of curvature is twice the focal length. Spherical mirrors form images in two main types: concave and convex. Concave mirrors create different images based on object placement. At infinity, the image is a tiny, real, upside-down point at the focus. As the object moves closer, the image changes. Beyond the center of curvature, the image shrinks. At the center, it's identical in size. Between the center and focus, it enlarges. At the focus point, no image forms. Between the focus and mirror's pole, a bigger, upright, virtual image appears. Convex mirrors form images behind the mirror, always virtual and upright, and smaller than the object. Concave mirrors are used in torches, headlights, and solar furnaces. Convex mirrors are used as rear-view mirrors and store security mirrors, showing a wide field of view with smaller images. Physicists use the new Cartesian sign convention with spherical mirrors. The mirror's pole is the origin point. Distances to the right are positive, and those to the left are negative. Heights above the principal axis are positive, and those below are negative. Objects are placed to the left of the mirror. The mirror formula is 1 over v plus 1 over u equals 1 over f, where u is object distance, v is image distance, and f is focal length. Magnification compares image size to object size. It's calculated as image height to object height, or image distance to object distance. Magnification determines if an image is real and inverted, or virtual and upright, and whether it's enlarged or diminished. Refraction occurs when light changes direction as it travels from one transparent medium to another. This can be seen in everyday situations, such as a water tank's bottom appearing raised or a penciling water looking displaced. Two laws govern refraction. The first states that the incident ray, refracted ray, and normal lie in the same plane, and the second, Snell's law, describes the ratio of the angles of incidence and refraction. The refractive index of a medium compares the speed of light in a vacuum to the speed of light in that medium. Different materials have different refractive indices, such as air, water, crown glass, and diamond, with values ranging from 1.0003 to 2.42. Lenses are transparent materials with two surfaces, at least one being spherical. There are two main types: convex and concave lenses. Convex lenses are thicker in the middle and bring light rays together. Concave lenses are thicker at the edges and spread light rays apart. Key terms for understanding lenses include the centers of curvature, principal axis, optical center, principal focus, focal length, and aperture. The optical center is the central point of the lens where light rays pass through without bending. The principal focus is where parallel rays meet or appear to originate from. The focal length is the distance between the optical center and the principal focus. The aperture is the effective diameter of the lens's circular outline. Convex lenses form different types of images based on object placement. At infinity, the image is small, real, and inverted at the focus point. As the object moves closer, the image changes. Between the focal length and twice the focal length, the image is enlarged, real, and inverted. At twice the focal length, the image is the same size as the object, real, and inverted. Concave lenses always produce small, virtual, and upright images, regardless of object placement. For drawing diagrams, 3 rules apply. Parallel rays pass through the focus, rays through the focus emerge parallel, and rays through the optical center pass through unchanged. The sign convention for lenses is similar to spherical mirrors. Measurements are taken from the optical center. For convex lenses, the focal length is positive. For concave lenses, it is negative. The lens formula is 1 over v minus 1 over u equals 1 over f. This formula relates object distance, image distance, and focal length. Magnification describes the size of an image compared to the object. It can be calculated using image height to object height or image distance to object distance. A negative magnification means a real image. A positive magnification means a virtual image. The power of a lens describes how much it bends light. It's calculated by taking 1 divided by the focal length in meters. The unit of measurement is called the diopter. 1 diopter equals a lens with a 1 meter focal length. Convex lenses have positive power, converging light. Concave lenses have negative power, diverging light. When multiple lenses are combined, their powers are added together algebraically. This concept is used in eye exams, camera design, microscopes, and telescopes. It also helps engineers minimize optical defects in instruments. Lens power is crucial in various practical applications. The radius of curvature of a mirror equals twice its focal length. The mirror formula is 1 divided by v plus 1 divided by u equals 1 divided by f. Magnification is image height divided by object height or image distance divided by object distance. Refractive index is the speed of light in a vacuum divided by the speed of light in a material. Snell's law describes how light bends when passing from one medium to another. For lenses, the formula is 1 divided by v minus 1 divided by u equals 1 divided by f. The power of a lens is the inverse of its focal length. Mirrors and lenses form images differently. There are 3 main types of mirrors. A plane mirror creates virtual and upright images, the same size as the object. A concave mirror can form real or virtual images, with size changing based on object placement. A convex mirror produces virtual upright images, always smaller than the object, but with a wider field of view. Lenses use refraction, not reflection. Convex lenses can produce real or virtual images, inverted or upright, with varying size. Concave lenses form virtual upright images, always smaller. Both mirrors and lenses can produce real or virtual images, with conditions differing. Reflection and refraction have many practical uses. Convex mirrors are used in vehicles as rearview mirrors, giving a wider field of view. Concave mirrors are used in solar furnaces to focus sunlight. Dental and ENT mirrors use reflection to view hard-to-see areas. Headlights and torches rely on reflective surfaces to direct light. Refraction also has important applications. Spectacles and contact lenses correct vision by bending light. Microscopes, telescopes, and cameras use lenses to magnify objects. Fiber optics transmits light through thin fibers, enabling fast communication and medical procedures. In gemology, understanding refraction helps cut and evaluate diamonds to maximize brilliance. Light travels in straight lines and behaves predictably. When it hits a surface, it can reflect or bend, known as refraction. There are two types of spherical mirrors, concave and convex. Each forms images based on geometry. The mirror and lens formulas connect object distance, image distance, and focal length. Magnification shows the ratio of image size to object size. Different materials bend light differently, measured by refractive index. Lens power is measured in diopters, with higher numbers indicating stronger lenses. Sign conventions are important for consistent calculations, ensuring results match observations. These concepts form the foundation for understanding light's interaction with mirrors and lenses.